Unit 1, 1D Kinematics. Introduction to Engineering Design. Engineering is the application of science to design products or inventions that meet human needs. Engineers invent technology that could make the future cleaner, safer, healthier, and more productive. It is in our common human interest for everyone to understand the basic engineering design principles. There is no one right answer in the engineering design process. There may be many designs that achieve the goal. What is the engineering design cycle? The first step is to come up with a design concept. Goals are first identified, then complicated goals are broken down into smaller goals that can be solved with a subsystem. Next, the design is made real with a prototype. The prototype is then tested and evaluated and revised. This process is repeated many times before the product is finalized. New technology may look very different from the original design. Since there is no one right answer, there are 4 challenges to the design process: creating something that has not existed, the complexity of the design, making difficult choices, and compromising between sometimes conflicting requirements. What is physics? Physics is the branch of science that describes the fundamental aspects of how our universe behaves. It describes the basic forces, the nature of atoms and matter, and the processes by which matter and energy interact. Mechanics is the branch of physics that deals with forces, objects, and motion. Mechanics develops and applies mathematics to describe the physical world using concepts such as velocity, force, and acceleration. Kinema means movement in Greek. Kinematics is the science of describing motion using words, diagrams, numbers, graphs, and equations. The goal of kinematics is to develop models that can describe the motion of objects. Some types of motion we'll be talking about this year include linear motion. The objects move in a straight line. Circular motion. The objects move around the outside of a circle. Projectile motion. The object is thrown into the air. And rotational motion. The object moves around a fixed axis. Describing motion. We can describe motion using quantities or models. A model is the relationship between variables used to determine an unknown based on what you know. Graphs are simple forms of models that relate to variables. Motion is described using quantities that are either scalars or vectors. Scalars are quantities that only have magnitude. For example, speed, temperature, and distance. Vectors are quantities that have both magnitude and direction. For example, velocity, displacement, or acceleration. Magnitude means size. Velocity is the speed and the direction of a moving object. Speed is the rate at which an object moves. We can draw vectors. They have 3 parts: the head, the body, and the tail. Remember, vectors must have a direction. The arrow points in the direction of the force or motion. The length of the vector represents the magnitude, how fast or how far, depending on the type of vector. If we look at these 2 vectors, you can see that they represent different velocities, so they are different lengths. With distance vectors, an east, right, or north, up direction is considered positive. A south or west direction Motion diagrams. Motion diagrams represent the motion of an object in several different times. Motion diagrams help us to focus on the overall motion of the object. From a motion diagram, we can tell if an object is moving and if it's speeding up or slowing down. To draw a motion diagram, you will draw 3 to 5 frames of the position of the object. To start, you place the object in the initial position. The next frame should show where the object moved in a given time. If all of the frames showing the object are an equal distance apart, the object has a constant speed. If the object is not moving, there would be just one frame. If the object is speeding up, the frames will show the object further apart in each frame. If the object is slowing down, the frames will show the object closer together. To show the velocity of the object, you would draw an arrow in the direction the object is moving. The arrow length should correspond to the velocity the object is traveling. A longer arrow means the object is traveling faster. To show acceleration, in a motion diagram, you would draw one arrow. The direction of the arrow tells you if this object is speeding up or slowing down. If the object is speeding up, the arrow is in the same direction as the motion. If the object is slowing down, the arrow is in the opposite direction of the motion. Particle diagrams are simplified models in which we assume all the mass of the object is concentrated at one point. This helps us focus on the overall motion of the object. We say that particles have position and mass, but they do not have size or volume. Particle diagrams are the same as motion diagrams, except you use a dot to represent the object instead of an image. Place the dot to indicate the distance the object would have traveled. Then, draw arrows for velocity and acceleration. Move it, move it. Let's look at distance and displacement. Distance and displacement seem like they mean the same thing, but they have different definitions and meanings. Distance is a scalar quantity. It refers to the total amount of ground covered. So, how far did you go? Displacement is a vector quantity. It refers to how far the object is from the starting position. So, let's look at an example. Miss L works at the local high school. She leaves her house at 7 a.m. and goes to the coffee shop before class. She arrives at the school at 8 a.m. She left the school at 3 p.m. to go to the grocery store and grab some snacks for her class. She arrived home at 5 p.m. What is the total distance that she traveled? So we'll add the total distance that she traveled, starting with the 1 kilometer to the coffee shop, the 3 kilometers to the salon, the 5 kilometers from the salon to the grocery store, and the 3 kilometers from the grocery store to the high school. On the trip home, she has the 3 kilometers from the high school to the grocery store, the 5 kilometers from the grocery store to the salon, 3 kilometers from the salon to the coffee shop, and 1 kilometer from the coffee shop to her house. So this gives us a total of 24 kilometers as the distance that she traveled. Now, what is her displacement at 8 a.m.? She has the 1 kilometer from her house to the coffee shop, the 3 between the coffee shop and the salon, the 5 between the salon and the grocery store, and the 3 between the grocery store and the high school. So this gives us 12 kilometers at 8 a.m. The last question, what was her displacement at 5 p.m.? Well, we already know that at 8 a.m. she had traveled 12, so now she travels back to her house. So this time she has a negative 3 kilometers, a negative 5 kilometers, a negative 3 kilometers between the salon and the coffee shop, and a negative 1 kilometer between the coffee shop and her house. So her displacement is 0 kilometers. Graphing motion. We graph motion to make motion easier to understand. A graph is a simplified model of the motion. What kind of graphs do we have to show motion? We can plot position time, velocity time, or acceleration versus time to show motion. The position time graph is the most simple graph. Time is always plotted on the x-axis, and distance is plotted on the y-axis. The further up the graph, the farther from the starting point. If an object is at rest, then you would graph a straight line on the position time graph. So a block is at rest 8 centimeters from the edge of the table. So if we graph this, we will have a horizontal flat line. If the object is moving at a constant velocity, you would draw a straight line with a slope that is equal to the velocity of the object. The steeper the slope, the faster the object is moving. A block starts at the edge of a table and it moves 16 centimeters in 10 seconds. So at 0 seconds, it is at the 0 position. At 10 seconds, it's at 16. And it's a straight line because the velocity is constant. You can also find the average speed or average velocity by using the graph. How do we find the average speed? To find average speed, we use the equation average speed equals distance over time. To find the average velocity, we use the equation average velocity equals change in position, displacement over change in time. Velocity time graphs. What would a velocity time graph look like? The velocity time graph still would have time plotted on the x-axis. The velocity is plotted on the y-axis. The further up the graph, the faster the object is moving. Let's look at the block again. A block starts at the edge of a table. It moves 16 centimeters in 10 seconds. We need to know the average velocity. We will use the equation v equals change in position over change in time. So 16 divided by 10 seconds gives us 1.6 centimeters per second. To the right. We've already created the position time graph, so let's create the velocity time graph. Since the velocity is constant and the object isn't changing speed, the velocity will be a straight horizontal line. Let's graph another example. This time, the block begins to move at 1 meter per second for 6 seconds. Then it is whacked and moves at 3 meters per second for the next 4 seconds. On the position time graph, for every 1 second, it moves up 1 meter. At 6 seconds, it begins to move at 3 meters for every 1 second. So you can see that it started moving slower the first 6 seconds. This next 4 seconds, it's moving faster. In the velocity time graph, it was at 1 meter per second for the first 6 seconds, and then at 3 meters per second for the next 4 seconds. So we have 2 different lines on the velocity time graph. Acceleration time graphs. If objects are speeding up, they are accelerating. Acceleration is a vector quantity that is defined as the rate at which an object changes velocity. Acceleration can be positive, the object is speeding up, or negative, the object is slowing down. Let's look at how all three types of graphs would look for the same situation. A toy car is accelerating at 2 meters per second squared from rest. The position and velocity are shown below. So in the position time graph, we have a scale of 10 meters on the y-axis, and we are going to plot those distances. At 0 seconds, it was 0 meters. At 1 second, 1 meter. 4 seconds, 16 meters. And at 10 seconds, it was 100 meters. So this graph has a curve. In the velocity time graph, we're going to plot the velocities. So at 0 seconds, the velocity was 0. At 1 second, it was 2 meters per second. At 3 seconds, it was 6 meters per second. This gives us a line with a slope of 2, which is the velocity. The acceleration time graph, the acceleration was constant at 2 meters per second, so it is a horizontal line at 2 meters per second. Let's look at an example with a negative acceleration. A car has an acceleration of negative 1.2 meters per second squared. The position and the velocity are shown below. So this time the car is slowing down. So we can go ahead and plot the position time graph. And as we do, we can see that this has a curve going down towards the x-axis. In the velocity time graph, it starts at 12 meters per second, and then in 10 seconds has slowed to 0 meters per second. And this gives a straight line with a slope of a negative 1.2. The acceleration time graph has a horizontal line at negative 1.2 meters. Remember, in velocity time graphs, if the line is moving towards the x-axis, the object is slowing down. If the line is moving away from the x-axis, the object is speeding up. Frame of reference in relative motion. The frame of reference is the object that we pretend is completely still. Why do we need a frame of reference? Without a frame of reference, there is no way to know how to answer a question about motion. Imagine you were trying to determine how fast a dog was moving. If the dog was moving at 5 meters per second, would you also include the speed of the Earth rotating at 416 meters per second? Or the speed Earth moves around the Sun at 30,000 meters per second? Or the solar system moving at 20,000 meters per second? Or the galaxy moving at 230,000 meters per second? This is why we need a frame of reference. Normally, we pretend that the Earth is still and we are looking at the motion in relation to the Earth. So an object is in motion if its position changes compared to the point of reference. So look at the dragonflies below. Determine the velocity of each dragonfly and the flower based on the flower's frame of reference. So the flower is at 0 meters per second. So the blue dragonfly would be moving at 2 meters per second east, while the pink one is moving at 1.4 meters per second west. Now determine the velocity of each dragonfly and the flower based on the pink dragonfly's frame of reference. So now we're going to say that the pink dragonfly is moving at 0 meters per second. That means that the flower is moving towards the pink dragonfly at 1.4 meters per second east. And the blue dragonfly is moving at 3.4 meters per second east. Now, determine the velocity of each dragonfly and the flower based on the blue dragonfly's frame of reference. So this time, We're pretending like the blue dragonfly is what's still. So the flower is now moving towards the west at 2 meters per second, and the pink dragonfly is moving at 3.4 meters per second west. When solving problems in physics, we're going to just guess. This doesn't mean you'll just write down an answer. This is the method we'll use to solve problems in physics. GUESS stands for givens, unknowns, equations, substitution, solution. This is what you will write for every problem you solve. It may seem a little silly right now because the problems are pretty easy, but it will be very important later. Let's look at a problem using GUESS. If a caterpillar moves 8.8 centimeters in 4 seconds, what is its average velocity? Our givens are x equals 8.8 centimeters and t equals 4.0 seconds. Our unknown, or what we're looking for, is the average velocity. Our equation that we're going to use is v equals the change in position over the change in time. Now we substitute what we know for our variables and then solve. So v equals 2.2 meters per second. Calculating velocity. Remember, the formula for average velocity is v equals the change in position over the change in time, or displacement over time. Another equation for calculating velocity is x final equals x initial plus velocity times time. X would be your distance. Let's look at an example. At what velocity did a plane fly if it traveled 1,480 meters in 12 seconds? So our given are the displacement at 1,480 meters and time at 12 seconds. We are looking for the velocity. The equation that we would use is velocity is equal to displacement over time. So now we substitute v is equal to 1,480 meters divided by 12 seconds. So the answer is velocity is equal to 120 meters per second. The cheetah is the fastest animal in the world. Scientists have recorded their speeds at 33.5 meters per second. Cheetahs are not able to maintain their speed for very long. If a cheetah ran at 33.5 meters per second for 25 seconds, what would be its displacement? So our givens are the velocity at 33.5 meters per second and time, 25 seconds. We're looking for displacement. So the equation is velocity equals displacement over time. We're going to rearrange our equation before we substitute. So then we get displacement is equal to velocity times time. So d is equal to 33.5 meters per second times 25 seconds. So the displacement is 837.5 meters. Remember your significant figures, so 840 meters. At the snail races, snails race on a straight 2-meter track. If the winning snail takes 153.8 seconds to cross the finish line, what was his velocity? So our givens, we know the displacement, which was 2 meters. The time was 153.8 seconds. And we are looking for the velocity. So velocity is equal to displacement over time. So we substitute 2 meters divided by 153.8 seconds. And velocity is equal to 0.013 meters per second. Let's look at the equations to calculate acceleration. The first one has velocity, final, initial, acceleration, and time. You'll use this if you're not given distance. In the second equation, you have displacement, the initial position, the initial velocity, acceleration, and time. Use this if you don't have final velocity. And the last equation gives you the velocity, final and initial, acceleration, and distance. Use this equation if you're not given time. Let's look at some examples. A cheetah is able to reach a maximum speed of 33.5 meters per second, that's 75 miles per hour, in just 3 seconds. What is the acceleration? Make sure that you box in your notes and underline what you're looking for. So our givens, our velocity is equal to 33.5 meters per second, and time equals 3 seconds. We're looking for the acceleration. The equation that we're going to use is V final equals V initial plus A times T. The initial velocity is 0. So our equation would be V final equals AT. Now we need to rearrange that equation so we can solve for A. So A is equal to final velocity divided by time. Now we're going to substitute. A is equal to 33.5 meters per second divided by 3 seconds. So A equals 11.16 meters per second squared. When we look at our significant figures, you can see that that is 11 meters per second squared. Make sure you put a box. The trap jaw ant, Odontomachus borii, is able to close its jaw in 0.13 milliseconds. If the ant moves its jaw 0.47 millimeters, what is the acceleration of the ant's jaw in meters per second? In the problem, we're given 0.13 milliseconds and 0.47 millimeters. Since we need our answer to be in meters per second, we can convert these into meters and seconds. So to convert millimeters to meters, we're going to divide by 1,000 by using the conversion factor 1 meter is equal to 1,000 millimeters. Of 0.00047 millimeters. We do the same thing with milliseconds. So 1 second is 1,000 milliseconds. So we would get 0.00013 seconds. Our unknown is acceleration. So the equation that we're going to use is D equals plus velocity initial times time plus 1/2 acceleration times squared. Since the initial distance and the velocity are both 0, we can rewrite our equation with d equals 1/2 at squared. Now we're solving for a, so we need to rearrange our equation. So we'll divide both sides by t squared and multiply by 2. So a is equal to 2d divided by t squared. Now we substitute. A is equal to 2 times 0.00047 meters divided by 0.00013 seconds squared. So our acceleration is equal to 16,000 meters per second. Now, when you see a number like this, it's very important to make sure that this sounds reasonable. And normally it wouldn't. But in this case, this ant actually is capable of accelerations at 10 to the 5th. So this is a very reasonable answer. A drag race track is 402 meters. If the velocity of the car when it crosses the finish line is 89 meters per second, what was its acceleration? So our givens, we know the displacement, which is 402 meters, and the velocity, which is 89 meters per second. We're looking for the acceleration. So the equation that we would use is v final squared is equal to v initial squared plus 2ad. So we're going to solve for a. Our initial velocity was 0. So v final squared divided by 2d equals a. Now we can substitute. A is equal to 89 meters per second squared divided by 402 meters times 2. So A is equal to 9.9 meters per second squared. Free fall. When something is dropped, it can be said to be in free fall. Free fall means that the only force that is acting on the object is gravity. That means nothing is touching the object and there is no air resistance. If you throw a ball upward, this is still considered to be free fall. The only force that is acting on the ball is gravity, even though it's moving up initially. The acceleration due to gravity varies based on your location on Earth. Generally, it's considered to be 9.8 meters per second squared. For this class, we will be using 10 meters per second squared. A skydiver falls for 7.8 seconds. What is her velocity at this time? So we know the time, which is 7. And we know the acceleration due to gravity, which is 10 meters per second squared. We're looking for the velocity. So the equation that we're going to use is v final is equal to acceleration times the change in time. V final is equal to 10 meters per second squared times 7.8 seconds. So the final velocity is 78 meters per second. The second part of the question asks, what is the distance that she traveled? So we still have the same time and the same acceleration. T is equal to 7.8 seconds, and acceleration is equal to 10 meters per second squared. This time, the unknown is the distance, or displacement. The equation is d equals 1/2 acceleration times squared. So we can substitute 1/2 times 10 times 7.8 squared and the distance that she traveled was 300 meters. A ball is thrown straight up into the air with an initial velocity of 15 meters per second. How long is the ball in the air? So we know the initial velocity, which was 15 meters per second, and we know the acceleration, which is going to be negative 10 meters per second squared. We're looking for time. The equation that we're going to use is V final is equal to V initial plus A delta t. The final velocity is 0 meters per second. This is when the ball has reached the highest point and right before it starts to come back down. So now we need to rearrange the equation. V final minus V initial is equal to acceleration times delta t. We're looking for t, so V final minus V initial divided by acceleration equals t. Now we can substitute. 0 minus 15 meters per second divided by 10 meters per second squared equals t. Now acceleration is a negative 10 meters per second squared in this equation. So t is equal to 1.5 seconds. That's the time that it takes the ball to go to the top. So we need to double that to get the full time that the ball is in the air. So t is equal to 3.0 seconds.